Time to start. So, hopefully everybody had a good Wednesday. Today is Thursday, I think. So today we're going to be talking about concavity and the second derivative test. So it's going to be a test that you can use if you don't want to use the first derivative test. Okay? And concavity is going to help us if you want to be able to sketch a graph. For instance, concavity is going to be some vital information that you need to be able to sketch a graph, or in general, check what you're getting in, say, Desmos is actually the right thing, or if you maybe made a typo. So, concavity, very important stuff. So before we start, let's look at some announcements. You have homework due on Monday. It's going to be over first derivative test and second derivative test, and increasing and decreasing, and concavity. Okay, so hopefully we get through everything today that you'll have everything you need to do the homework. If not, then you'll definitely by Friday. Okay, and then exam 2 is next Friday, which is October the 23rd. I'm working on a review sheet right now that I will post probably over the weekend. Okay, so exam 2 next Friday. Okay, do we have any questions on either of these announcements? All right. Well then, let's talk about what we learned last time. So last time we learned about the first derivative test, which is a test that you can use to determine if a function has a relative maximum or relative minimum at a critical number. And it relies entirely on the properties of increasing or decreasing for a function. Okay, so let's look at an example really quick to remind us of what the first derivative test looks like in action. Okay, so classify the relative extrema of the function f of x is equal to the square root of 4x minus x squared on the interval 0 to 4. Okay, so I want to classify all relative extrema. So what's the first step to find any relative extrema?
Derivative.
Yeah, I'm going to take the derivative, right? I'm going to take f prime of x is equal to something. So this function here is a composition of two functions, right? We could rewrite this as 4x minus x squared to the 1/2. So to take the derivative here, what rule do I need to use?
Chain rule?
Yeah, I need the chain rule, right? So I need to use the chain rule, I need to know what is my outside function and what is my inside function. So let's do the inside function first. What's the inside function?
Four x minus x squared.
Yeah, exactly. 4x minus x squared. And then I need to know what's the outside function.
X to the 1/2.
Yes, perfect. X to the 1/2. Excellent. Okay, so with the chain rule, I need to take the derivatives of both of these. So what's the derivative of the outside function? What's the derivative of x to the 1/2?
1/2 x to the negative 1/2.
Perfect. 1/2 x to the negative 1/2. And what's the derivative of 4x minus x squared with respect to x?
4 minus 2x.
Perfect. 4 minus 2x. All right, so chain rule says the derivative of this composition is going to be the derivative of the outside. So 1/2 of evaluated at the inside. So 1/2 times 4x minus x squared to the minus 1/2 times the derivative of the inside. So times 4 minus 2x. There we go. So this is equal to then 4 minus 2x divided by 2 times the square root of 4x minus x squared. Okay, what do I want to do with this?
Set it equal to 0.
I want to set this equal to 0. Exactly. So I have this fraction equals 0. So what does that tell me?
The numerator equals 0.
The numerator equals 0. Perfect. So I get from this 4 minus 2x is equal to 0, which tells me that x is equal to 2. Do I get any other critical numbers from this? Yes, I do, right? Yes, thank you, Saba. Yeah, if we look at the square root, the critical numbers are where f prime of x is equal to 0 or f prime of x does not exist, right? When f of x does exist. So I need to also look at what happens when this is negative. When 4x minus x squared, or not negative, sorry, when 4x minus x squared is 0, because the square root of 0 is defined, but 1 over the square root of 0 is not defined. Okay, so I need to check for when 4x minus x squared equals 0 to see if there are any other critical points, or sorry, critical numbers that we get here. Okay. But when we factor the left-hand side, I'm going to get x times 4 minus x equals 0. So what does that tell me? What does this equation right here tell me? I'm going to get either x equals 0 or
X equals 4.
x equals 4. Excellent. Okay, but notice we're on the interval, the open interval 0 to 4. So I don't really need to include these as critical numbers because they're not in the interval. Okay, but you should always check for those types of critical numbers where the derivative is not defined, where the original function is defined. Okay. So I really have one critical number, x equals 2. So I need to make my chart to look at where is f increasing and decreasing, or where is f prime positive and negative. Okay, so what numbers are going to go on at the top of my chart? Definitely a 2. Anything else?
0 and 4, since they're the endpoints of the.
Perfect. Perfect. You need to, we're doing this between 0 and 4. Because again, those are the endpoints of the interval that we're considering this function on. Okay, so then all I need to do is I want to look at the derivative. Well, the numerator is 4 minus 2x. The denominator is 2 times the square root of 4 minus or sorry, of 4x minus x squared. And then f prime is the top divided by the bottom. All right, so what test point should I pick between x equals 0 and x equals 2?
X equals 1.
X equals 1, perfect. What sign does 4 minus 2x have at x equals 1?
Positive.
Positive, very good. What sign does 2 times the square root of 4x minus x squared have between x equals 0 and x equals 2? Or for x equals 1.
Positive.
Yes, this is also positive. Okay, so f prime is a positive divided by a positive. Well, that's going to be positive. So f is increasing between x equals 0 and x equals 2. So this is what f looks like. All right, what test point should I take between x equals 2 and x equals 4? X equals
3.
3. Excellent. So what sign does 4 minus 2x have at x equals 3?
Negative.
Yeah, negative. What sign does 2 times the square root of 4x minus x squared have between, or at x equals 3?
Positive.
Yeah, positive. Very good. So f prime is a negative divided by a positive is going to be a negative. And so f is decreasing between 2 and 4. So what kind of extreme value do we have at x equals 2?
Max.
Is a relative maximum. Very good. And the value of that relative maximum, well, f of 2 is going to be the square root of 8 minus 2 squared. So this is square root of 8 minus 4 is 4. Take the square root, I get 2. Okay. Questions? All right. So the first derivative tells us roughly what shape f has, right? We saw last week that if the first derivative is positive, f prime of x is bigger than 0, then that means f roughly has an increasing shape, right? It roughly looks like that. It might be doing some other stuff. It could be doing something like this, or it could be doing something like this, but it has to be increasing, right? And on the other side, if f prime of x is less than 0, then f has to have a shape roughly like this, right? It could be doing something like this, or it could be doing something like this, but it has to have a shape that's just roughly trending downwards, right? So with the second derivative with concavity, we're going to learn whether or not f has a shape like this, or like this, or like this, or like this. Concavity tells us, gives us the extra information of whether f is what's called concave up or concave down. And again, that corresponds to these 4 different shapes of a graph. So first we need a definition of concavity before we do anything with concavity. So we're going to let f of x be a differentiable function on the open interval I. So if you want, the I could be the whole real line, but if you want, you can just think of it as some open interval a to b. Okay. We say that the graph of f is concave up on I when f prime is increasing on the interval. Okay, so not when f is increasing, but when f prime is increasing on the interval. Okay, and we say the graph of f is concave down on I when f prime is decreasing. Okay. So f prime is increasing really means we know how to check if a function is increasing or decreasing, right? We just take the derivative of the function. But now we're checking where is f prime increasing. So I want to take the derivative of f prime. We'll see that in a second. That's how we're going to check for concavity, is looking at f prime prime. Okay. Really quick, let's look at the graph of a function where we can see where a function is concave up versus concave down. Okay. Your book, by the way, uses the words concave upward and concave downward. It's too much. I'm not going to use, it's a mouthful. I'm just concave up, concave down. Okay. So here's a graph of a function. Oh, could we say convex? No, not in this class. I'm not going to use the word convex in this class at all. But if you have seen what's called a convex function, you feel free to use the word convex if you understand what it means. Okay, so here's the graph of a function. I've marked in blue where it's concave up. I marked in red where it's concave down. Okay, so if we look here where it's concave down, here's a point where there's a tangent line there, right? The derivative, the first derivative, is the slope of this tangent line. So if I take another point over here, notice that the tangent line has a derivative that's negative. This derivative at that point, at this point right here, was positive, right? So f prime decreased from this point to this point. And if I take another point right here and I draw its tangent line in, then its tangent line has a slope that's even more negative than that tangent line, right? So this is what concavity is trying to get at, that the tangent line, the derivative, the slope of the tangent line is decreasing when you're on a concave down interval, and it's increasing, oops, that's a really bad tangent line, is increasing at those points where the function is concave up. Okay, this is the whole idea. And then at these points where the function changes from concave up to concave down, it actually crosses through its tangent line. Okay. So are there any questions about what concave up versus concave down means? So because it's defined in terms of the derivative of a function, it's something where you can't just talk about really the concavity at a point. It really has to be on an open interval where you're talking about concave up versus concave down. Just like with increasing and decreasing, that was also, we talk about that on an interval. It's the same thing for concavity as well. All right. So like I said before we looked at that graph, we know how to check where the function f prime of x is increasing, right? Because we know if I want to look for where is just a function, I'm going to call g of x a function really quick. If I want to check where this function g of x is increasing, well, that's the same thing as checking where is g prime of x greater than 0. Okay? But remember that f prime of x is just a function of x. So if I want to check where f prime of x is increasing, well, that's the same as checking where f prime prime of x is greater than 0, right? So I want to check for where f is concave up, which is where f prime of x is increasing. I want to check where f double prime of x is greater than 0. Or in other words, where f double prime of x is positive. And by the same reasoning, if we want to check where f of x is concave down, then we just need to check for where f double prime of x is less than 0. Okay? Or in other words, where f double prime of x is negative. This is how we check for concavity. Are there any questions about this? Does everybody see that checking that f prime is increasing is the same thing as checking where f double prime is positive? For the same reason that checking where f is increasing, you check where f prime is positive. All right, let's look at an example. Let's find the open intervals where the function f of x is equal to e to the negative x squared. Let's find where that is concave up or concave down. Okay, so I'm checking for concavity. So what do I need to find in terms of f?
F double prime.
Yeah, I need to find f double prime. So to find f double prime, there's no way around it. I have to find f prime of x first, right? So how do I take the derivative of e to the negative x squared? Yeah, that's a chain rule problem. So what function is my outside function and what function is my inside function? Well, what's the inside function here? What was it?
X squared.
Yeah, negative x squared. Perfect. And then what's the outside function?
E to the x.
E to the x. Perfect. And then I need to take derivatives of both of these. Well, what's the derivative of e to the x?
E to the x.
E to the x. Perfect. What's the derivative of negative x squared?
Negative 2x.
Negative 2x. Perfect. All right. So the chain rule says to take the derivative of this function, I need to take the derivative of the outside evaluated at the inside. Okay. So I need e to the negative x squared. There's the derivative of the outside evaluated at the inside. And then I need to multiply by the derivative of the inside. Negative 2x e to the negative x squared. Very good. And then I need f double prime of x. Okay, so now I need to differentiate negative 2x e to the negative x squared. Okay, so how do I take the derivative of negative 2x times e to the negative x squared?
Product rule.
Yeah, that's the product rule, right? So with the product rule, I'm going to take the derivative of minus 2x. Well, that's just minus 2. And then I'll leave e to the negative x squared alone. Plus, then I'm going to leave minus 2x alone. And then I'm going to take the derivative of e to the minus x squared. But what's the derivative of e to the minus x squared?
Negative 2x e to the negative x squared.
Perfect. We already did that derivative, right? We already took that derivative right there. So we already know that that's minus 2x e to the minus x squared. Very good. So simplifying this, both of these have an e to the minus x squared. I'm going to factor that out. E to the minus x squared times, well, when I factor out the e to the minus x squared there, I get minus 2. And then plus, I'll be left with minus 2x times minus 2x is plus 4x squared, right? All right. And so I need to check where is this increasing and where is this decreasing, right? So what should I do with this then?
Set it equal to 0.
Yeah, I'm going to set this equal to 0 because in order to find where it's positive and negative, I need to first find where it's 0, and then we'll do what we did for the first derivative, but now for the second derivative. Okay. So I need to solve e to the minus x squared times 4x squared minus 2 is equal to 0. Well, this is a product of stuff. Is e to the negative x squared ever equal to 0?
No.
No, this is never equal to 0. So I need to solve 4x squared minus 2 is equal to 0. Well, I can add 2 to both sides, plus 2, plus 2. I get 4x squared is equal to 2. I can divide by 4. So I get x squared is equal to 1/2. And so I get x is equal to the square root of 1/2 plus or minus. Okay. Which I'm going to write as plus or minus 1 over the square root of 2. All right, so I want to find where f prime is increasing or decreasing, which means I need to find where f double prime is positive or negative. Okay, so where is f of x defined? When I make this table, what should I have along the top?
Negative infinity to positive infinity.
Good. I'm going to have negative infinity and positive infinity. Okay. And then between these, I'm going to have minus 1 over the square root of 2 and plus 1 over the square root of 2. Okay. So then the second derivative is e to the minus x squared times 4x squared minus 2. And then we have f double prime. All right. Well, what sign does e to the negative x squared have for any x?
Positive.
It's positive everywhere. E to the minus x squared is positive for any old x. Okay. So we don't even need to pick test values there. We can just fill in that whole row with pluses. All right, what test value should I pick for x between minus infinity and minus 1 over the square root of 2?
-1.
-1, very good. -1. Cool. So what sign does 4 times -1 squared minus 2 have?
Positive.
That's positive. Very good. So f double prime here is a positive times a positive is going to be a positive. Okay. What test value should I pick between minus 1 over square root of 2 and plus a square root of 1 over 2? Sorry, plus
0.
1 over square root of 2. Yeah, x equals 0. Very good. So what sign does 4 times 0 squared minus 2 have?
Negative.
Is negative. Very good. So f double prime is a positive times a negative is a negative. And then what sign does, clearly we're going to pick x equals 1 over here. What sign does 4x squared minus 2 have when x is 1?
Positive.
Positive. Very good. So f is concave up where? And by the way, I always shorten concave up as CCU. Concave up. Well, f is concave up where f double prime is positive. So where is that going to be?
Between negative infinity and -1/2, and or 1 over square root of 2, and then 1 over square root of 2 to infinity.
Perfect. And where is f concave down? Gotta add a page for a single. F is concave down. Where? Well, f is concave down where f double prime is negative. So where is f concave down?
From -1 over square root 2 to 1 over square root 2.
Good. Excellent. All right, so notice I didn't draw the shape of f underneath this table like I do when I have the first derivative, because just knowing f double prime doesn't let me know if f is increasing or decreasing. Okay, I would need to first find where f prime is positive or negative, and then go from there. Okay. Cool. All right, another example, find the open intervals where the function f of x is equal to x squared plus 1 over x squared minus 4 is concave up or concave down. All right, what do I do here?
Find the derivative.
Find the first derivative. Very good. So how do I take the derivative of this function? X squared plus 1 divided by x squared minus 4?
Quotient rule.
As a
Quotient
quotient
rule?
rule. Very good. So quotient rule says I need low d high. So low is x squared minus 4 times d high. What's d high?
2x.
2x. Very good. Minus high, x squared plus 1. By the way, on the last exam, I saw a lot of pluses here. Remember that this is a minus in the quotient rule. Okay, so minus high d low. What's d low?
2x.
2x. Very good. Over the square of what's below. So over x squared minus 4 squared. All right, so this is equal to, after simplifying a little bit, 2x cubed minus 8x minus 2x cubed plus 2x over x squared minus 4 squared, which is equal to the 2x cubes cancel, right? So I'm left with minus 10x over x squared minus 4 squared. All right, and then what do we do now that we have this?
Take the second derivative.
Yes, exactly. I need to take another derivative, right? I need f double prime of x to check for concavity. And how do I take the derivative of this thing?
Quotient rule again.
Yes, that's again the quotient rule. Very good. So low here is going to be x squared minus 4 squared, x squared minus 4 squared times negative 10, which is d high, right? Times negative 10 minus high, negative 10x, d low. Well, how do I take the derivative of the bottom here?
Chain rule.
Chain rule, very good. So I'm going to write it out quickly so to save some time. So you're going to get 2 times x squared minus 4 times 2x over the square of what's below. So x squared minus 4, x squared minus 4 squared squared is going to give me to the 4th, right? Okay, well, let's simplify this a little bit. This is x squared minus 4 squared times negative 10 plus 10x times 4x times x squared minus 4 over x squared minus 4 to the 4th. All right, and notice that up top, both terms have an x squared minus 4. So I'm going to factor that out. I'm going to get x squared minus 4. When I factor that out, I'm going to be left with negative 10 times x squared minus 4, because this was squared, so I have one of them left, plus 10x times 4x divided by x squared minus 4 to the 4th. So now that the whole top is being multiplied by this, I can cancel that with one of these. Okay, and so after simplifying, we're going to get, well, this is 40x squared, and I'm going to do minus 10x squared is going to give me 30x squared, and then plus 40 divided by x squared minus 4 to the 3rd. Okay, any questions on this second derivative? Yes, I can see all chats, public and private. So let's then, I need to add a page. So let's then look at the sign of this. The sign of this function here tells me where f is concave up or concave down, right? So f prime is 30x squared plus 40, or was that, yeah, 30x squared plus 40. Divided by x squared minus 4 to the 3rd. Okay. Does this have any critical numbers, this function here? Or in other words, sorry, does this have any place where it's equal to 0?
No.
No, because if this equals 0, that means the top is equal to 0, right? But if 30x squared plus 40, if that's equal to 0, then 30x squared equals negative 40. So that x squared is equal to negative 4 over, well, negative 40 over 30. So negative 4/3, right? But I can't have something squared be negative. So this has no solutions. So when I make my table, what numbers should go along the top? Well, where is this function back here defined? Where is that function defined? It's almost all real numbers. It's definitely, I'm looking at the interval negative infinity, but is there any place where f of x isn't defined?
X equals 2.
Yeah, x equals plus or minus 2, right? If the bottom is 0, f is undefined. So you need to include those in your table because the behavior of f, even though there's not any critical numbers there technically, or any place where f double prime is 0, because f is undefined there, the behavior of f could change at x equals plus or minus 2. Okay, so at x equals plus or minus 2. So minus 2 plus 2, and then we go to infinity. All right, and then f prime or f double prime is the top divided by the bottom. Okay, so what sign does 30x squared plus 40 have for any x?
Positive.
Positive.
Is positive, right? It's got to be bigger than 40. So plus, plus, plus. All right. So what test value should I take between -2 and negative infinity?
-3.
Yeah, -3. Perfect. What sign does x squared minus 4 to the third have at x equals -3? Which is really just going to be the same thing as the sign of x squared minus 4.
Positive.
Positive. Very good. So f double prime is positive on this interval. What sign does x squared minus 4 to the third have for x between -2 and 2? Well, let's check at x equals 0, right? At x equals 0, we're going to get -4 to the third. What sign does that have?
Negative.
Negative. Very good. Okay, and over here at x equals 3, what sign does x squared minus 4 to the third have?
Positive.
Positive. Very good. So where is f concave up?
Negative infinity to -2 union 2 to infinity.
Perfect. And where is f concave down?
-2 to 2.
-2 to 2. Perfect. Are there any questions on this example? So one of the takeaways from this is you need to check for where f double prime is equal to 0 or where f double prime doesn't exist, but you also need to include in this table those points where just f is undefined. Okay, so at the top of the table, you should have points where f double prime is 0, where f double prime doesn't exist, and also where f itself breaks. Okay. So there are special points back here, right? There's, for this example, at x equals -2, we have a switch of concavity, and at x equals +2, we have a switch in concavity. Okay, in this example, we had a switch in concavity at x equals -1 over the square root of 2, and at x equals +1 over the square root of 2. Okay, so for that first example, really not the second example. For the first example, those points where f switched concavity are called points of inflection. Okay, for a point of inflection to exist, we need f to exist at the point. So that's why on this example, -2 and +2 are not points of inflection because f of x is undefined at those points. Okay. So points of inflection are points on the graph of f where f switches concavity. Okay. They're important to plot when you're making a sketch of a graph by hand. They have to occur where f double prime is equal to 0 or f double prime fails to exist. But just because f double prime of x or f double prime of c is equal to 0 for some c does not mean that there's a point of inflection at c f of c. Okay, so it's just like with critical numbers. Just because f has a critical number at some x doesn't mean necessarily that f has a relative max or a relative min there. It's the same way. So points of inflection, f double prime of x equals 0 is where you check for points of inflection, but they're not necessarily where f has a point of inflection. Okay. So points of inflection are where, if I come back to the graph back here, they are where this graph switches from red to blue. Okay, it's where the graph switches from concave up. People say where the graph is concave up, the graph will hold water, and where the graph is concave down, the graph would spill water out. If you imagine this graph of a function as a weird sort of cup. Okay, so concave up and concave down. That was right here. Okay. So, are there any questions about point of inflection? It's got to be where it's not just where f double prime is 0, is where f switches concavity. So, really quick, find any points of inflection for the function f of x is equal to 4x cubed minus 12. I'm going to run through this really quick. So, we need to find first f prime of x. Because we, again, points of inflection have only to do with concavity. So I need to get to the second derivative. So f prime of x is 12x squared minus 12. And then f double prime of x, well, that's going to be 24x. And that's it, right? So where does f double prime of x equal 0?
When x equals 0?
Yeah, when x is 0, right? So this function is defined for all real numbers. So when I make this table, I'm going to go minus infinity to 0 to infinity and beyond. So f double prime of x is just 24x, right? So what sign does 24x have for x less than 0? Let's say x equals -1.
Negative.
Is negative, right? And what about for x equals +1?
Positive.
Positive. So f is concave down from negative infinity to 0. F is concave up from 0 to infinity. So that means that 0, comma, f of 0, which is 0, 0, is a point of inflection. Okay. So a point of inflection is an actual point. You want to give an x and a y value. Okay, but it occurs at x equals 0 because that's where f changes from concave down to concave up. So are there any questions about points of inflection or concavity?
So just to make it like clearer for me,
Yeah.
like the point of inflection would essentially be like where our relative maximum or minimum would be, or on like the
That's a good question. Not necessarily. A point of inflection is going to occur. Actually, most of the time, it's not going to be a relative max or relative min for f. A point of inflection is really, either a relative maximum or a relative minimum for f prime. Okay, but not for f. And so we just think of it as it just has to be where f changes from concave up to concave down, or from concave down to concave up. Does that help?
yeah, it does. Thank you.
Cool. Yeah, any other questions for me? If you don't have any questions, feel free to sign off, and I'll see you guys tomorrow. If you do have any questions, feel free to stick around, and I'll answer any questions you might have.
Thank you.